So for today's session, here you go. I am going to be giving you an introduction to R, but I wanted it to be more interactive. So we're going to actually work with some data, okay? And we're going to do some network visualization a little bit, just a little bit, okay? If we have enough time. If not, we can continue in another time. For sure, I'm going to try to do this once every while, depending on the needs. Regarding the workshops, the other workshops, so people from Network Canvas, they confirm they do have like an big opening, in I think it's October, because they were trying to do like a big workshop there. But I guess that if we want it earlier, we could. We just need to gather a sufficient, a large enough group of people, so it's worthwhile for them to give the workshop, because they do have people. Their team, I think it spans not just the US, so they have people in the UK maybe, and I don't know. It's every time that they do this, they do have some cost associated, at least with time. So, okay, so let me start with the very basics. R, it's a programming language, right? It's the successor. Sorry, is that the word? Yeah, it's what came after the S programming language. Okay, that's the original one. S, that's the name for, and I think it was named. Was developed in the Bell Labs, and it's because statistics is as far as I understand. And then it was named R because I think is that the following letter? No, it's the previous letter. I don't know why it was named R. I don't remember, but there's a story behind it. There are plenty of books out of there. I am recommending here The Art of R Programming, but a newer reference I would suggest is taking a look at the book that's called R for Data Science by Hadley Wickham. It's a free book. You should take a look at it. Okay, they teach you R from the very basics to more advanced stuff, and it's great. The only thing I don't like a little bit is that it's very opinionated, because this book uses the tidyverse mostly, and the tidyverse is a collection of R packages, very opinionated R packages that people created to ease pipelines and work in R. It's great, but the only part that I don't like about it is that it's too heavy in dependencies. So anytime that people talk about efficiency in installing R packages, they talk about the tidyverse because it has so many dependencies that it takes very long to install. And having a lot of dependencies in software, meaning that, I don't know, your program depends on other programs, introduces a lot of possibilities for your program to fail, to break. So it happens sometimes that a version of some package in the tidyverse fails on CRAN, which is the main repository of R packages. And because of that, all of the other packages that depend on that fail as well. And that's not nice. So that's one of the things that that's the main thing I would say I don't like it. Other than that, it's a great alternative. I do have a lot of examples with this in the book. But nowadays, if you ask me, what do I use for like processing data in R, I'm more into the data table package, if you ask. So the data table R package, it's great. It's a great alternative to tidyverse, because tidyverse is mostly for data management. With the difference is that it has zero dependencies. It has no dependency whatsoever. It's amazing for big data. So if you are into bioinformatics, for example, Jiawen, you will find that data table is one of the most efficient tools that are out there for data management. So you can handle millions of columns in fraction of a second, millions of rows, and I don't know, it's amazing. So take a look at it if you haven't. Okay, let's continue. So in R, as you know, we have packages, right? So we don't call them libraries, it's called packages. In R, a library is where we store packages. And that's just a dumb stuff thing. But the correct way to describe a software component extension of R is package, no library. But again, it's just semantics. I don't know. It doesn't matter. But because of that, people say packages because they use install packages. Sorry. Sorry, I'm always slipping myself. Yeah. So people call it libraries because in every other programming languages, the extensions you call them libraries. In R, they are called packages. And how you install them, you just type install package and then the name of the package that you would like to install. So for example, here's how you will install NetDiffuser in R. Okay. And the other thing about R is that we do have in R this thing that's called CRAN, okay, which is it's just it means the comprehensive R archive network. And it's an international network of computers that stores a replicate of R and the packages that it comes with. Okay. As of today, I think there are about 17,000 R packages out there. The cool thing about CRAN, and this is one big difference with Python, is that whenever you want to submit a package to CRAN to be shared with the world through this platform, it needs to go through an extensive list of checks. The packages need to be checked. They have to be well documented. There must be no errors in the software. If you have, for example, you should have examples in your functions. They also check for dependencies and a bunch of other stuff. So the thing is that this is like a quote unquote like a manually curated list of 17,000 packages that have to pass machine tests and human tests, like people inspecting them, which is very cool because in other programming languages that's not the case. For example, in Python, you can go ahead and like upload to the PyPy. I don't know what's the name of it, the Python equivalent, but you can just upload almost anything, but it's not checked by anyone. Whereas in CRAN, things are checked, which is amazing. Okay. And oh yeah, I do have the instructions how to like get R, and I'm using right now RStudio in general, which is an IDE, integrated development environment for R. So you can just go ahead and use the old-fashioned command line if you like, or R comes with a GUI, which it's kind of like not very nice. Or you can use RStudio, which is great. I do use it a lot. And they even have like a server version, so you can take a look at it. So I'm going to skip that for now. Okay. So before we start, I'm just going to like go through these slides very quickly. It's a quick and dirty introduction to R. You can go over it later on. Okay. So first of all, the first thing that you need to know in R, and I would say that almost nobody learns as a first step, is how to get help. How to get help is fundamental because, as I just mentioned, all the packages on CRAN are humanly curated. And because of that, every function that comes within an R package must be documented. So have a description of the input variables, of the output variables, and examples. So if you don't know how to use a function in R, for sure you just need to go and check out the manual, and that's it. And how can you get help in R? Well, you can just type question mark the name of a function, or question mark double quotes the name of a function. Okay. They will both take you to the read.csv function help, or type help, which is a function in R, and like this, right? If you want to go and look for a concept rather than a particular function, and I don't know, you want to look for GLMs or whatnot, you can use the help search function like this, or the double question mark and then the concept. So let me show you in R. Give me 1 second. I'm going to I wasn't sharing the entire screen. I'm going to share the entire screen now. Okay, so here I am. I'm going to do it in the command. I'm going to use RStudio later, but for now, I'm just going to show you how does it look in the command line. So when we start R, it looks like this. Okay, it will tell you at the top the current version that I have. And by the way, 10 points for whoever can tell me where do the code name come in R, because every R version comes with a code name, okay, and they have like funny code names. Does anyone knows about it? Are users out there trying? Do you know? This comes from Charlie Brown, the Snoopy. Uh, every other version, their code names come from Snoopy and Charlie Brown's episode names. So if you Google this, you will get a Charlie Brown episode. That I don't know, but I find it funny. Okay. Okay, so let's take a look at it. So if I look for help here, it's not going to look very nice, but just for you to know. For example, as I was saying, if I want to get help about how to read a function, I just type a question mark and read CSV. This is how to read a CSV file. See, and it will show you a very detailed help file, as you can see here. Right? So what are the components of a help file? Well, you first have the description. It will show you always a description of the function. Okay. The usage, usage section will show you all the ways that you can call the function with its arguments and the default value. So, for example, if I just call read table, which is another function in the set of read plain text files, yeah, I can just, for example, I can just go ahead and say and type like let me jump between lines. I can just type read table and then the path to a file, I don't know, my file.csv could be, and it will work, right? But the thing is that whenever you're calling this function, by default, it's going to have all of these other arguments. So by default, it's going to assume that there's no header, so header false. It's going to assume that there's no separation between columns, how codes are defined, so on and so forth. The same with read CSV. Every time that I call a function read CSV, I can just type the file name with quotation marks like I'm doing here, right? But it will also assume that there's a header, that the separation is a comma, right? CSV file, that makes sense. The decimal mark is a point, and that's important if you're not from the US, my case. Decimals in Chile are not points, are commas, actually. So, and so on and so forth. After the usage, it comes then the list of arguments. So each one of the arguments has a definition or an explanation, and it will tell you, okay, so file, well, the name of the file, which the data are to be read from, right? So it'll tell you how you can specify it, so on and so forth. Header, a logical value, so it's either true or false, indicating whether the file contains names. The separation, so on and so forth, and it will give you a detailed description of all of its arguments, and that's with all our functions, okay? Well, this should be the case. And then it will show you some details. And it will like give you an more extensive description of what the function does and some details sometimes that are missed. So for example, it tells you, okay, the read.csv and read.csv2 are identical to read table with the exception from the defaults. So essentially these two functions are what's called a wrapper of read table. The defaults change. And after the script, the details, you will see value. Okay, and what's value? Well, what's the output of the function? It will either, most of the cases, functions will return something. I don't know, it could return a new number, a new variable, a transform vector, whatnot. Or it could have a second, what's the word? Or something could happen in the environment. For example, when you call plot, when you call the function plot, it will like open a visualization device and it will like show you a figure. So that also should be described in value. And there's sometimes they might include some other more information. And finally, and this is one of the most important bits, examples. In every R function manual, you will see this section, examples. And this is literally showing you how to use the function, right? And the examples in general are executable. So which means that if I run all of these lines of code, they should work. Right, let me show you. I have another session open here. I'm going to like copy and paste this code here. And it went through, no error. So it worked. And that's because the example sessions will always show you code that works. And sometimes it will tell you, okay, you will see a little comment here that will say do not run. But that's not very common. Okay. Okay, so in not looking for help is very important. If we, for example, want to read about social networks, you can look for that like this. So this is a concept now, it's not a function. I could type double question mark social networks. If I go here, it will try to like show me whatever it finds. And what found is the SNA package. Okay, help files with alias or concept matching social networks. The SNA package. Okay, and that's for like and if you want like more point and click and you are working on a command line tool, you can always type the function, which I haven't included here, help.start. Help.start will open the browser and show you this. So you can go ahead and like point and click. I don't know, I want to go to the packages and I want to get help on iGraph. So yeah, make it for or NetDiffuser, which is a package that I wrote. And it will show you this like this, and it's with colors also. It's prettier, and you will have links around, and you can run examples. And yeah, so that's with help.start. Okay. Now in R, and again, I'm sorry, I'm going to kind of like just fly by this a little bit. You can go in detail later, and you can copy and paste the code that we're going to be using later on as well. In order to create objects, we have two like baseline functions, which are the assign operator, which is just a left arrow, or the equal sign. So for example, in this case, these two are equivalent. If I type that in my R session, if I type a arrow 1, I just create an object with symbol a that equals to 1. So if I type a and press enter, it will show me the number 1. Then if I type a, I can replace this, and this is text. You can also do this. Okay, so now I'm assigning the string, this is text, to a. So if I type a, it will print this is text. See? And the same will happen if instead of the assign symbol, I use the equal sign. It also works. Okay. But the equal sign is discouraged because when you call functions in R to specify the arguments, you use the equal sign as well. So to avoid the confusion, I would recommend, and in general, people recommend to use the assign symbol instead. Any questions so far? No? Okay. Yeah. This is just, and this all the objects that I just printed are scalars, meaning that it's just a atomic number. It's just a single element object. Okay, but in R we can have more complex things, like for example vectors. If I want to create a vector that has numbers from 1 to 9, I can do it like that. So if I type just like this, 1 colon 9 in R, it will create a vector from 1 to 9. And if I type 9 colon 1, what do you think I will get? Anyone? Will it work? Well, it should work. A vector from 9 to 1. So it's just the reverse. And we can assign it to an object, right? So we can say A, assign like that. And if I print A now A is a vector from 9 to 1. Here, what I have is, since I put it on parentheses, anytime that you put a parenthesis around an operation in R, it will just print it out explicitly. So as you can see, I first created here the vector, and then I type A. Right. So by the way, you guys are seeing my command line, right? Okay. I can get this, but I can actually do these two steps at once by just wrapping it around parentheses. If I do this, it will print it out, while at the same time assigning the value to A. Okay. Oops. Yeah, you can also create vectors like this. So to create vectors, you concatenate values. That's the name of the function. The C in R is concatenate. So you can create vectors like, I don't know, 1, 10, 2. This is a vector with 3 numbers, or it could be with letters. A, L, W. It also works, see? We can also have matrices and which just kind of like fly over this. This is how you create a matrix in R. So the matrix function, you can pass a vector and then specify the number of columns it has. And you will get an output like this. You can create a matrix. Matrices are also supported for strings. So in this case, the first matrix I created here is a matrix of integers, right? Oops. Sorry, I forgot to create a vector. Let me do it on the fly. 1 to 9. And but also they can be made of strings. See. Then another important function in R is the column-bind function, cbind. Okay. So what it does is that it will take 2 vectors and paste them together, bind them, right? So for example, I have vectors 1 through 4, and then vectors 4 to 8, 4 to 7. And I can then column bind them. 1 to 4 and 4 to 7. Okay. So if I type this, I will get a matrix, right? Because since I'm pasting together 2 vectors, the result is a matrix of 2 columns. And you can do this with multiple of them, right? So it's then 7, 10. I have 3. See? And the same happens with rows. If we do R bind instead of C bind, R bind is for row binding. So I will like paste them one over the other, one under the other. So we get the reverse. See, so 1, 2, 3, 4, 4, 5, 6, 7. This is R bind. And then we have lists. Lists are collections of objects, which could be anything, right? So for example, let me show you. I can have a list of a number, a vector, and then a matrix. 4. See, this list has 3 elements. First element, second element, and third element. The first element is just number. The second is a vector, and the third is a matrix. So you can combine a bunch of elements using lists. Okay, and you can even give them numbers. For example, or names. So let me, in this example, again, so you have all of these examples here. I'm just giving you additional. So for example, this is, let's call this A, let's call this B, and let's call this last element C. So elements in bits can be named. So instead of having like this 1, 2, 3, when I create a list using names, you will get something like this. This is A, this is B, and this is C. And the nice thing of lists is that then you can access its elements in various ways. So the first one is, for example, we can access them by name directly using the $sign. For example, if I want to get to the element A, I just type $A. See? If I want to get to C, $C. Right? Or you can even like use the name as a string. So if this is another way, $A and double square bracket quotation mark A are equivalent. And since A is the first element of my list, my list is like this. If I type my list double square bracket, I will get the same first element. So there are many ways of accessing elements. Okay. And finally, we have data frames. Okay, data frame is the structure I would say you are mostly familiar with. So this is the equivalent to a data set in Stata. Okay, raw matrix. So whenever you read a data in Stata, in R, this is equivalent to a data frame. And a data frame is kind of like a matrix that may have like multiple types of data, so that you can have numbers, strings, or other types of data. But they have you have a fixed number of rows and columns. So for example, if I type this into R, data frame X equals to something and Y equals to something else. So these are just numbers. Okay, so Y column you can call like this, H whatever, you can put whatever you want. You will get a data frame that looks like this, which is your data set ultimately. Okay. Any questions so far? No? Okay. Now, for the sake of time, I'm going to skip all of this. The next section talks about how can you like access elements in general in vectors, in matrices, in lists, and in data frames. So I'm going to skip that a little bit. And then the next section talks about like what's called control flow statements. For example, for loops, okay? And whiles, all the stuff that you may not need. And finally, I'm also going to skip this a little bit. You can take a look at this by yourself. This is one of the most important things in R, which is generation of random numbers. Okay. Actually, let me go quickly through this part because it's important. R has a great pseudo random number generation function, like library, embedded in C. A lot of other packages and like and actually people has go so far up to use R embedded in their C code to like generate random numbers because they have such a great way to do this. Okay. In R, the convention is that for any distribution, you might find 4 different functions. Okay. One for generating random numbers, one corresponding to the density function, one to the CDF, and one to the inverse, to the quantile function, the inverse of the CDF, right? And the way that they name these functions in R, it will be something like R for random number generation, and then the name of the distribution. So for example, if you want to think about uniform numbers, the function to generate random uniform numbers is called R unif, or uniform. For random normal numbers, it's called R norm. For binomials, it's called R binom, right? So you will, by all of them starts with the letter R because that's for random. The density function is D. So the density of a uniform is D units. Of a normal, D norm, so on and so forth. The cumulative distribution function, this is a bit different. It's P, and I'm guessing it's because of probability, okay? So if you want the probability of a normal, P norm, or of uniform, P unit, so on and so forth. And for the quantile function, it's Q. So it's very straightforward. Q norm, Q unit, so on and so forth. Since we are dealing with computers, random numbers in computers do not exist. I don't know if anyone has told you that, but random numbers in computers do not exist, okay? The right way to call them is actually pseudo-random numbers, because they are not entirely random, they are kind of deterministic, and they are deterministic because they depend on a seed number. And that's good because if you want to have reproducibility, if you want to give people to be able to like reproduce your code, if you're doing simulations, you can always have to set up a seed. And in R, we do it with the function set seed, set.seed, okay? In this case, I'm just saying, you can use any number. So you can use 1 to 3, 1, a million, whatever number, but it's just the baseline number that the simulation engine will use to simulate random numbers. And here, I'm just showing you some examples. Here, I'm just simulating 100,000 uniform numbers in R. So I use the R unique function. I'm creating these 100,000 numbers, assigning it to X, and then plotting the histogram of it. If I want to do 100,000 normal random numbers, I can use just R known 100,000 and then call hist, and I will get this. If I want to change the mean and standard error, so it's not anymore like standard normal, it's just normal. You can do it like this, R norm, and then the mean and standard error parameters. here's a Poisson, random number Poisson distribution, exponential, so on and so forth. And if you want to get more help about this, you can go and check out the distribution help file in the manual. Okay. Okay. Any questions so far? No? Okay, guys. So now we're going to jump to the fun part.
Yeah, I do have a question. So when are we going to using this random number stuff? If we have a data set, usually we won't using this simulation, right?
Sorry, how's that? I didn't get your question. Oh, she froze, I think. Okay, we'll wait for her. But let's continue in the meantime. So I'm going to jump to part 8. Okay, so for this page, we're going to be using these R packages. If you don't have it, you will want to install them. It shouldn't take that long, okay? We're going to be using Ergom, SMA, iGraph, Intergraph, Netplot, NetDiffuser, and RDepset. But you can go and uninstall them if you need them while we're working on it, okay? So we're going to be talking about simulating random networks and plotting them. Why simulating them? Because I was looking for a graph that we could use that could be fun, but I actually, unfortunately, wasn't able to find any in these last 2 days. So we are just going to simulate one. When it comes to random graphs, I think about them as there are like 3 different categories in random networks. Okay, you have the exogenous ones, the endogenous ones, and the exponential random graph models, like more a general version. By the way, this is my categorization. I didn't got this in from any book. I've been thinking about this, but feel free to like take it or not. But this is just a way to explain. Exogenous networks are those that are determined by an exogenous rule, like a macro rule. And by that, I mean, for example, when you want to have an expected degree distribution, meaning that you want this many nodes to have this degree, and so on and so forth. Or you have a degree sequence. So you want node 1 to have this in and out degree, node 2 to have this in and out degree. So there are ways to specify that. But the bottom line is that they depend on a predefined macro rule that governs everything. Okay. So it goes from the macro to the micro, somewhat. Then you have the endogenous, which are the opposite, meaning that you have a rule that is determined at the node level when it's creating ties, but then because of this, it has a property that expands to the macro level. One canonical example are scale-free networks, okay? Scale-free networks are determined mostly by preferential attachment, meaning that nodes tend to be connected to, you have just a handful of nodes that have a very high in degree, and most of them have like very low in degree, so it's like a long tail distribution, okay? But that property comes from the micro level, because when nodes are creating ties, they will tend to link to nodes that have higher degree, like the most connected degrees. So it goes from inside to outside. That's why I call it endogenous. And then you have ergoms, which you have heard me talk about. And ergoms actually can encompass any of these models. I won't go into details, but I'm a preacher of ergoms, and that's why, because ergoms are like a general form of all of these other models, okay? And because of this, we're going to be using ergoms to generate a random graph, okay? So the graph that we're going to be...
Sorry, the question is in the chat now, the one that...
Oh, thank you. Okay, now I'm seeing it. Awesome. When using simulation data in a study, and there are a bunch of examples like that. So Jiawen asks, can you give us an example of when using simulation data in a study? I would say that most analysis that depend on, for example, complex data structures will use simulations, because there's no way in many times to write down a likelihood, like try to write down exact probability function. And in that sense, any non-parametric method that you're using uses simulation. For example, bootstrapping, which I'm sure that most of you have heard about at least one time. So we use bootstrapping because sometimes we are not sure about the distribution And we cannot get, we are not sure that the standard errors that we're getting are the correct ones. So what we do is that we just resample. And when you're resampling, you're essentially running a simulation, because to do that, you have to generate random numbers. And that's a simulation. So Bootstrap, it's basically a simulation. That's one example. Oh yeah, so Emery has a great question. So she says, can I use install dot packages and name all of the names that you need to install them? Well, yes, but not in that way. So if you want to install multiple packages at the same time, what you need to do is, I'm going to show you, is to type install dot packages parentheses. So you're starting the function, but then you have to build a list, concatenate a list of strings. And then you say C parentheses quotation I graph, and then, for example, I don't know, data table. And by doing that, you will be able to install, like in this case, 2 packages. You're telling R to install these 2 packages. I'm going to put it in the chat. So that will work. Okay, but that's a great question. Okay, Joanne, did I answer your question? Great. Let's continue. And thank you, Karen, for letting me know about the chat. Okay, so yeah, going back. So we're going to be using algorithms. And in this case, we're going to do a fun model. I'm going to simulate a social network in schools, in a school in particular, okay? And for this, I'm going to base the simulation on 4 properties that we have seen many times in studies across social networks. First of all, networks tend to have low density, meaning that people tend to have just a handful of connections. Even if you have a huge, I don't know, an entire country, the number of connections does not scale with the size of the number of individuals, but rather people tend to have like a somewhat fixed number of friends and family members, right? We have low densities in general. But then we are going to build the graph based on homophily, like the tendency of individuals to connect based on some shared feature. But in this case, based on race homophily, meaning that individuals who have the same race seem to befriend each other. Okay, we're going to base this network on structural balance as well, which is also known as triadic closure. Okay, or as I like to say it, the friend of my friend is my friend. Okay, so that's going to be another property that will govern the data generation of the graph. And finally, we're also going to be using homophily on age, meaning that, okay, so it's less likely for 2 individuals of very different age to be friends, but rather individuals who have a closer age are more likely to be friends, okay? So we are going to be using these 4 properties. And to do this, let me use this and by the way, let me actually, I should have said this earlier. You can actually download the R script that generated all of this. So you can copy and paste it directly. So I should put an easier way to link this. If you go, you can, if you want, I put there a link. So if you go to that web address, you will download the R Markdown file that I'm using to generate this. Okay. So and you can open that in R. Or if you want to actually look it on the website, you can also click here. That's not to download, but actually to look it on GitHub, which is where I keep the files. Okay, so I just realized, okay. So let me continue. Okay. Yeah, and actually let me do this with you. So I'm going to open this on RStudio. Yeah, so it will open this. You can then download it. So left click on Save As. And I'm going to keep it on my downloads. Save it like that. And then from RStudio, if you're using RStudio, which I think it's one of the easiest ways to do it, you can go ahead and then open the file and it will look something like this. So I'm going to do it myself. I'm on RStudio right now. Open file. Actually, let me start a fresh session of RStudio. So in RStudio, go to File, Open File, and then where do I have this thing? Let's locate the file line, and then open it, and you should get something like this. Okay, so I just opened this is the same file we're actually looking at right now. Okay, so I'm going to be using this now. Any questions so far? And if you have any questions for later on, you are like redoing the session, please email me. I know that it's difficult, but all that I can tell you is that you will just learn with practice. It just takes a lot of practice. Okay, there's no other way to learn this kind of stuff. It's a steep curve, but it's worthwhile. Okay. Okay, so let's continue. So this is what we're going to be doing. So again, so resuming, I just said that we want to generate a network with these features, right? And the steps to do so are the following. First, we're going to simulate a population of n students. In this case, we're going to pick 200 and randomly distribute race and age across them. Once I have this synthetic set of individuals with their features, I'm going to create an empty network object. And by empty, I mean that it's going to be an empty graph with no ties whatsoever. But then I'm going to take this empty network and use the Ergon package to simulate a graph. Okay. So how do we do that? So first of all, since this is like random number generation, we use the setSeed function, right? And let me do it here so you can see it together live. So first I run this line, setSeed. So now we have a seed, so you can actually get the same results that I'm getting. Next, I'm assigning 200 here, so n is going to be equal to 200. And by the way, can you guys see it? Is the size appropriate for you? Or anyone wants me to increase the size?
I'm okay.
Great. And then I'm going to use a very handy function that's called sample. And what does the sample function do? Well, it does exactly that. It will sample from something. In my case, I'm just going to take a random sample of a vector with 2 elements, white, non-white. It should be maybe no white, I don't know. And then I'm asking the sample function to take n number of sample draws from this vector of 2 elements with replacement. Okay. If I don't put replacement, the R will complain because it's going to tell me, okay, how do you want me to get 200 elements without replacement for a set that only has 2 elements? That's not possible. Okay, so that's why you have to put replacement true. So we're going to be doing that. So let me just run it so you can see what I get. So now I get a race vector, a string vector that looks like this. So you have a vector with 200 elements that it's just shuffle version of non-white, white, white, and white. And the same with H. We have H here, right? And I just picked 3 numbers, 10, 14, and 17. Okay, so we have individuals from like middle school and high school, right? Now, to simulate the graph, I'm going to be using 2 R packages. Okay, so I need the Ergon package, which I'm going to load using the library function. Okay, you will see a bunch of like information here that's printed out. That's not very important. And then the network package, which I think it's preloaded, but it doesn't matter. It's okay. And once I have that, the network package has a function that's called network initialize. And what does this function do? Well, let's see what it does. So I can actually look for the help, right? If I click question mark, network initialize in RStudio is going to like show me in here. They have like a help window here. Create and initialize a network object with n vertices, which is what we want. See? So by doing this, if I run this line of code, now I have a net object, which if I print out, it should tell me, give me some information. So in this case, it's a network with 200 vertices, but that has no edges whatsoever. Okay. But we do have 2 sets of attributes here that we would like to add. So how can we add them? Well, this is a network object from the network package, and they do have a way to access attributes of nodes. And how do we do that? Well, they have this operator that we call b. So if you anytime that I call this function b wrapped in a percentage symbol, it will access to a vertex attribute of the network. In this case, what I'm doing is I'm accessing the race attribute. If I type only this bit here, if I type net b race, it's NA, right? Because I don't have anything right now that's called race in this network. But since, as you can see here, I'm using the assignment operator, I'm now assigning the race vector I have here, right, to the network. And the same with H. Right, so just run these 2 lines of code. So now if I type net, the network object, what should I see? Well, I still have 200 vertices. I still haven't added any edges, but now I have this thing here. So where it says vertex attribute names, I will see 3 now. Before, if you remember, we only had 2, only one, sorry, which was vertex name. But now we have 3, age and race. So if I type this now, net vertex operator race, and enter, what should I get?
Race.
Yeah, the same race, but now with a value, right? So before it was an A, but now it actually has something because the vertices have these attributes here, right? So that's how we do it. So now that we have this empty network with individuals who have attributes, we can use ergons. And this is well, I think one of the most fun parts. I'm going to kind of quickly fly over it a little bit. So to simulate ergons, we can actually go ahead and use this function that's called simulate. Okay, and call it with a model that we want to simulate and the set of coefficients we want to pick. Okay, ergon is similar to logistic regression, so values in general are exponentiated. So you don't want to pick values like too big, right? Because values too big are going to make your network very dense or very sparse, which you don't want. So these numbers that I got here, coefficients for my model, I handpicked them like by trying. One at a time. So there's not much science. You could, in principle, try like calculate how dense you want the graph to be and find some values, but we're not doing that here. Okay, I'm not going to show that now, but this is how you can do it. So here, so right now, where are we going right now? What are we doing right now? So I'm going to simulate a graph with the simulate function from the ergon package, and the result is going to be assigned to an object that's going to be called netsim. By net simulation, right? So for this to work, we have to pass a formula. And what's the formula like? Well, the formula has 2 sides, the left-hand side and the right-hand side. In the left-hand side, you used to have the network object, which we already have by net. Then squiggle, which means distributes. That's the idea of formulas in R. Then in the right-hand side, you should have the ergon model that you want to simulate, okay, which amounts to the terms you want to include. In our case, we said that we wanted what? We're talking about density, homophily on race, balance, and homophily on race. What did I add here? Density is edge count, so I'm going to specify a particular parameter for edge counts. Race homophily, we're going to be using the term node match race. That's in ergon notation. Balance, which is triangle oh, actually, no, this is not, I messed up. It shouldn't be triangle. Triangle is something else. It's literally a triangle. I'm sorry. I had to change that, but okay, but let's handle it for that for a second. And finally, absolute difference in H. So what this term does is that it will, for each pair of vertices, it will take the absolute difference of H, okay, and use that as a term. And what are the coefficients that I'm using? Well, I said low density, so it has to be sparse. So to have a baseline low density, we have to have a negative number. -4 is going to tell the graph that it's going to be simulated to have a low density. Node match race, this has a positive value, so we want to have homophily on race. we have to have a positive value in triangles and balance. Whatever, it's not fun, but bear with me. And finally, absolute difference in H, so which is homotopy and H. Okay. By construction, absolute difference will compute differences, right? So if the value is big, it means that you have a big H gap. But we want to have the opposite. We want to have homotopy. We want individuals who have small H gap to be friends. So for that to work, this term has to have a negative coefficient, and that's what I'm doing here. Okay. So we have simulate the formula. I run this. Let me rerun this from the beginning, all of that. Once I run this, now if I type netsim, what should I get? Well, I still have a network of 200 individuals, but now we have 463 edges. So we just simulated a graph, okay? Now the next question is, how does it look like? Okay, and I'm explaining what I'm doing here step by step, so you can then go over it, see? So I try to do that. To see how it looks like, let's use the gplot function, which stands for graph plot from the SNA R package. Okay, so I'm going to call this function library SNA. I have here, right? Library SNA. I loaded the library, and then I call the function gplot. If I call this, I should get a pretty network. See? This is how our school network looks like. We do have a few isolates there. It seems well connected, but I'm noticing something here. Oh, I'm using white. Bad choice of color. No. If you notice here, we have 1, 2, 3. You'll see what's that. Okay, but I'm not going to jump ahead on myself. Okay, it's already 11, but let me continue just for a couple of minutes. If you want to leave, I'm recording this so you can see it later if you can't stay any longer. And again, if you have any questions later on, you can always write me, and I am more than happy to help. So let me just jump ahead a little bit. Okay, so now that we have this, we can now plot the figure. And just for you guys to see the punchline of this, what I'm going to do next, I'm going to plot this, okay, using different functions. In between, another thing that I did, I'm not going to show you right now in detail, is I did an exercise in which I actually took this network that I just generated and stored it as plain text file, so we can actually later on read it. Okay. That's just for the practice of it. I will go back into this at some point in the future, because reading networks is also very important, but I'm just going to skip it for now. Okay. Let me jump ahead. That part. Let me skip this. Okay. For visualizing, we have 3 main features. Okay, for visualizing networks, which are we have three features in general. So we have the node size, how big are the nodes, node shape, and node color. Okay. Vertex size is kind of difficult to pick because it could be hard depending on the agent that you're using. And what I mean with difficult is because you can get results like this. Okay. If you don't know how to pick exactly what's the size of the vertices, you can get like nasty things like this. Here I was just trying to set different vertex size in network. Okay. So I got from the very large to the very small, to things in between. Using as a reference for the size, the in degree. Okay. Let me jump ahead so I can just show you one complete example so you can see how you can do it. Okay. Let me jump ahead a little bit. Okay, this is what I want to show you. If you take the graph that we just simulated, okay, which is this netsim, okay, and you'll have to like run the code above. I'm going to be using two features for this network. First, the vertex color. Or actually, I wasn't using size, this color. Actually, just vertex color by default here. Okay, and what I want is I want to color this network based on age. And for that, I have a little trick here. Again, because of time, we can go over this later on some other point. But what I'm doing here is I'm just creating a vector of colors. Okay, let me show you how this thing looks like. Let me go ahead to my code here. Okay, so here I'm just picking up a vector of colors. Okay, here, this thing here I just created. It's a vector with names. So it has three values: gray, tomato, steel blue. These are the colors I'm picking. And the names are 10, 14, and 17, the names of the elements of this vector. And what am I doing this? Because I can use indexing, which I won't explain in detail right now, but the idea is that you can access elements in a vector based on their names. So for example, if I type these colors, and then I type quotation mark 17 like this, I should get steel blue. If I do 10, 17, I should get what? Gray and steel blue.
I think you missed that one quotation mark.
Oh, you're right. You got it. That's the one that I missed. So I should get this too. So you got the idea. So now if I use now the age attribute of individuals like this, I should get one color for each individual like that. So that's the idea. So now what I'm using here is I'm creating this vector of colors, assigning colors to each individual, and then using that value to add some color to the figure. So now this is how the figure looks like without doing anything. But now if I include this, now I get three colors. So what do we see here? Can any of you tell me what do we have here? What's the main thing that we have here? There are no wrong answers, so don't worry.
I see three groups.
Yes, three groups based on.
And they are tied together.
Yes.
And I think the tomato group, similarly, they were somehow mixed with the blue group.
Exactly, yeah, and that's because the way that we can build this network is that, if you remember, we set up age and gender homophily. And the effect that we're looking at here is actually clusters like modules based on age. And this is exactly what we wanted, see? So, which means that the ergon model that we used worked, because the way that we built it, again, we enforced age homophily. And it turned out to be three groups. So this is, and here, let me jump a little bit ahead. So here in this, at the end, I'm adding just a legend here. So the gray ones are individuals of age 10, tomato ones are 14, and blue ones 17 years old. And you can go further. I have another example you can go by yourself later on, in which I'm actually using shapes. So if we do that, I'm doing something similar, like I did before with color names. I'm using shapes based on the number of on the shape of the vertex. So if I run this line of code, I get this. And now I have raised white, non-white, see? And we have that it seems that, for example, triangles may tend to be together, right? You also see like clusters of circles here, 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 but usually they tend to be like clustered. And that's because also in the ergon model, we added homophily on race. But from what we see also, I believe that the strongest effect was homophily on age, okay? And that's it. that's all I wanted to show you for today. I'm sorry I went too quick. We will do more of this. I'll try to make it slower. And this is already online. So I'm going to add a little bit more of text. I already tried to like explain myself throughout in every example. So hopefully you find it useful. Okay. Any question? No?
Now I do have a question. I post in the checkbox about the sign, the V sign.
Oh, yeah. So that's for accessing, that's from the network library, yes. So if we can actually look for help with that, right? So if we're in R, right, R Studio or the command line, so you can use question mark and quotation like that. See? It takes you there, see? So extraction and replacement operators for network objects.
Thank you. This time I mixed the quotation sign. I could not find anything.
Oh, yeah. So because if you do this, yeah, and it will throw an error. And why is that? Because actually the percentage symbol, it's also, sorry, it has a meaning. Oops. No. Well, actually, it does not have a meaning. Double has a meaning. It's an arithmetic operator. But if I type it like this, I think it might not work. Yeah. So you have to be careful. It's always a good idea to wrap it around quotation marks when you're looking for help. Or if you're using our studio, you can just go ahead and here in the search box on the top, you can just type that and it should work. If I type that, it will work. If I type like this, it will work too. See? So yeah, any other question? Okay, guys. So I'm glad you came. And thank you very much. I will upload this as soon as possible. And again, I'll make sure I will add more text to the book. And if you have any comments, suggestions for the book, please let me know. This is a continuous work in progress. Okay. And yeah, that's it.